What?
The Fu Manchu on Eli?
Oh no, I think it'd be sweet.
You should get
He
like
wants
a,
you to
like a
embarrass
crazy
yourself.
I feel
Viking
like cut off
beard.
though like every day from now on, and aviators everywhere I go.
You got one.
Yeah.
All right.
You also need an aviator jacket.
So on
need an aviator
the
jacket.
yellow sheet that I just gave back, here's my concern. It was the question where it was like you're at the top of the loop and you want to feel half your weight, and what's the minimum velocity that you have to have? And here's my concern is that it's right, but a lot of you just said, oh, that's 3/2 grr, and you plugged in the numbers and you got your answer, okay? Here's my concern is that you didn't write down, and I give you credit for it, but here's my concern is that you have no idea where this came from. You blissfully wrote down 3/2 grr. You're going to get 2 points on an assignment that's worth 20% of your grade, and then you're going to get on the test and you're going to have absolutely no idea where this equation came from, okay? And it came from the idea that 1/2 FG equals force centripetal minus FG. So as you're going back and you're reviewing for this test, which by the way is going to be next Thursday, okay? I realize it's the night after Halloween. I don't care. I hate Halloween. So that's when this next big test is going to be. So my concern is that you're going to go back and you're going to study instead of out extorting people for candy. And it's true. And so then you're going to look at that and you go, wow, I have 3/2 grr and I have no idea where that came from. So just make sure that you understand that whole process on that particular problem. Okay, so yesterday we left off talking about this equation, F equals big G M1 M2 over D squared. Okay?
Sure you hate Halloween?
And trust me.
I just found this in your stuff.
What is it?
It's
Yeah, someone did
jack-o'-lantern.
Yeah, no, trust me.
I mean, it looks like you got it.
Shh. 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 Shh.
Maybe you're a warlock.
Yes.
The proof is in the pudding.
And there's a Halloween toy.
Okay.
Oh, man.
So, what do we call big G?
Gravitational constant.
Universal gravitational
Check this out.
constant,
That's it. Watch this.
which is 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared. There's 3 numbers that I would recommend that you store into the memory of your calculator because it's going to make life simpler. One is going to be this, the 6.67 times 10 to the minus 11. The other one is the mass of the Earth, and that's listed on the top left corner of your equation sheet, which is 5.979 times 10 to the 24 kilograms. And then the radius of the Earth, 6.3713 times 10 to the 6 meters. So I would store those into your calculator. You don't have to, but it's going to make life simpler if you do, okay? Especially this big G, because that's what we're going to use a lot, and we're going to use the mass of the Earth a lot. Those are the 2 most common ones. Like I said, if you want to punch them in every time, that's fine. But here's what you have to be careful of. When you're punching in this times 10, do not punch in times 10, okay? It's going to completely jack up your order of operations. Use that EE key or that EXP key. Don't use times 10. Bad things are going to happen if you do this. So, it's just a universal gravitational constant. So, we got this number. So, let's say, and this is what we talked about yesterday. So, we're going to take Landon, and we're going to say that Landon's going to have a mass of 100 kilograms. And the fire extinguisher, which is 5 meters away, has a mass of 10 kilograms. And then we're going to say that they are 5 meters apart. Okay? So we're going to go through and we're going to calculate the actual force between Landon and that fire extinguisher over there on the wall. Now, when we do this, do you think this is going to work out to be a very big number?
No.
No, it's going to be incredibly small, right? So And trust me on this one, in this unit, you have the capacity to get answers that make absolutely no sense. Like if you forget to square something or cube something or take the cube root of it, like one of the things you're going to calculate is the amount of time it takes the Lunar Command Module to orbit around the moon. I have literally seen answers in seconds longer than the universe itself has existed. Okay? Literally, like the universe, if I did the conversion, I took the number of seconds that the student gave me and converted it into seconds. The universe has not existed that long. Okay? On my AP physics class, I got an answer for the amount of time it took for something to orbit around the Earth. It was like 10 to the negative 12th seconds. Nice. Okay? Yeah, but they realized it was wrong. This is what I found out. They realized it was wrong, and then they put a little question mark off to the side. It's like, I'm going to write down an incredibly stupid answer, but I'm going to put a question mark on the side, so that'll make it okay. No! Okay? No. Putting question marks off to the side doesn't make your wrong answer less wrong. Okay? Oh,
It's surrendering. It's accepting the fact that like.
Yeah, Nick's used to that.
yeah. Okay.
Get him.
All right. So, what you're going to forget to do, trust me on this one, you're going to forget to multiply, or you're going to forget to square root of 5 or something like that. This is where things are going to go south. So, has somebody actually run this number and let me know what you get?
2.668 times 10 to the negative 9th.
So, call it 2.67 times 10 to the negative
9th
newtons. Okay? That's a pretty small number, right? It's calculable, but probably not enough that's going to make any difference. So in the middle of a lecture, I don't have to worry about the fire extinguisher starting to hover and then accelerate towards Landon. It'd be cool, don't get me wrong, but it's probably not going to happen. But here's what would happen. If you could put Landon out in deep space, okay, 5 meters away from the fire extinguisher, okay? That would be the force between them. Now, who exerts the greater force? Landon or the fire extinguisher?
Landon. Neither.
Neither. It's the exact same. What's Newton's third law?
For reaction is equal.
For a reaction, there is an equal and opposite reaction. So, you felt that. And so, the force exerted on both of them is going to be the same. Will they both accelerate at the same rate?
No.
What's going to accelerate faster, Landon or the fire extinguisher?
Fire extinguisher.
Fire extinguisher will. Now, this is where this gets kind of a circle. They're going to begin to accelerate towards each other, so they're going to close the gap. As the gap gets smaller, this distance is going to become smaller. So what's actually going to happen to the force between them as they begin to drift towards each other?
It'll get greater.
It's going to increase. But then as they get closer, the force increases. But as the force increases, what's going to happen to the acceleration?
It'll increase. Right?
The acceleration is going to increase, which is going to make them close the gap even farther. So it kind of becomes this catch-22. Okay? So the closer they get, the more force there is, the more they accelerate, the faster the gap. So it kind of becomes this like double integral for those of you that are calculus nerds. Okay, now let's talk about this number right here. Isaac Newton was a big idea kind of guy. He says, look, I'm just going to lay this whole thing out. I'm going to let somebody else do the nuts and bolts of this whole thing. So all Newton said was this. He goes, if you have two objects, Landon and the fire extinguisher, the force that exists between them is proportional to their mass. So if the fire extinguisher was also 100 kilograms, there'd be more force. It's inversely proportional to the distance squared. So as the distance gets greater, the force gets smaller. Okay? That's all that you have to know about that. He actually never came up with a numeric value of G. He just said, look, there's some constant of proportionality that exists in this equation. I don't know what it is. I've got other things to worry about. I'll let somebody else do the hands-on work. So that was left to a guy by the name of Henry Cavendish. And what Henry Cavendish did was pretty clever. He took something what was known as a torsion wire. So torsion wire can twist, but it will only twist with a known amount of force to make it twist. So this is a torsion wire. This is like a big crossbar. and then he put a big lead weight here and a big lead weight here, and then he brought another big lead weight to each side. And what he noticed was that these began to attract and the wire began to twist. So what he did is he went back to this equation, Newton's equation, big G m1 m2 over distance squared. So he had measured how much force it took to twist the torsion wire. So he knew F. He knew how far apart the lead spheres were, so he knew distance. He knew the mass of each one, so he knew these two values. So the only thing he didn't know was big G. So Henry Cavendish was the first one to measure the value of big G. Now, his equipment was so precise that he actually did this. He had a room built onto his house and had this built out there. And he was afraid, because this stuff was so sensitive, that he was afraid that his own body mass would affect the experiment. So he actually stood outside the room and had the experiment run, because he didn't want his gravitational field to interact with the system because it was that sensitive. So he was the first one to get a numeric value of G. Now here, and later on you'll see how he used this, but once he figured out the numeric value of G, he was able to find the mass of the Earth. So that was Henry Cavendish's big claim to fame. I was the first one to weigh the Earth. We've known the circumference and diameter of the Earth, but we never knew the mass of it, because it isn't like, oh, let's take the Earth and put it on a scale and we'll get a reading. Okay, there, we got it. Okay, now we'll put it back in orbit and life's good. Okay? So, and it isn't like, there's a plate somewhere buried in the Andes Mountains where it has the information on how the Earth was made. Made on this date, here's the mass, here's its density, here's how plate tectonics work, here's how penguins evolve. Okay? There is no plate that has that information. We've had to figure this all out. So, once we got that value of G, then we were off to the races. So, let's go back to this calculation. Whoa. And that force is 2.67 times 10 to the negative 9. So, Landon says, hey, I'm kind of feeling the attraction towards the fire extinguisher. I'm going to get up and I'm going to walk towards the fire extinguisher. Okay? So, he's going to move, and instead of being 5 meters away, he's going to be 2.5 meters away. So, we're going to do this exact same calculation. But F equals 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. Now, when you move, is that going to change your mass?
No.
Is it going to change the mass of the fire extinguisher?
No.
Nope. But now we're going to divide by 2.5 meters squared. So somebody run the numbers again, but just divide, instead of dividing by 5, divide by 2.5. And
1.06. Do you want to enter 3 significant digits?
Yep, what'd you get?
Okay. 1.07 times 10 to the negative 8.
So, what's happened to the amount of force between Landon and the fire extinguisher?
Increase.
It's increased. Why?
'Cause
The distance is
small.
small. Now, Honus, out of curiosity, take 1.07 times 10 to the negative 8 and divide that by 2.67 times 10 to the negative 9.
Good. Divide that by 2.67.
Yep, times 10 to the negative 9.
Okay. Okay. 4.01.
So 4. So this is 4 times greater. Now, it's a shocking fact that if you reduce the distance by half, the force becomes 4 times greater.
No.
Why not?
Because it's squared.
Squared.
Because it's a squared function, right? So here's the deal, and this is more of like a pure mathematical approach. This was the first calculation, m1, m2 over d squared. Okay, so that was our first one we did with 5 meters. Okay, it doesn't make any difference. This was just my initial set of calculations. So if I reduce the distance by half, that becomes still big G, M1, M2, but now I want to have distance over 2 squared, right? Distance over 2 squared. So this becomes big G, M1, M2, D squared over 4. So the flow 4 is going to flip up. So if I reduce the distance by half, my force goes up by a factor of 4. Now, let's say then it goes, you know, that's kind of creepy. You know, I'm kind of going to do this just weird. So he goes, I'm going to go over and I'm going to sit over here on the other side of the room and I'm going to make the distance instead of 5 meters, I'm going to make it 10 meters. So this is if we reduce it by a half. And Landon goes, I'm getting freaked out. So he goes, I'm going to double the distance, okay? I'm going to move twice as far away. I'm going to move 10 meters away. So then what's going to happen to the amount of force?
It's going to get small.
By what factor?
4.
Now it's going to be a fourth as much, and here's the reason why. I've still got the same big G, M1, M2, but now it's going to be 2D squared. So 2D squared becomes 4D squared. So that's like saying it's 1/4 of big G, M1, M2 over D squared. So if the distance gets, if you double the distance, the force goes down by a factor of 4. If you reduce the distance by half, the force goes up by a factor of 4. Now, Landon, what if you triple the distance? What's going to happen to the amount of force?
By a factor of 9.
Yeah, it's going to go down by a factor of 9. If you reduce it by a third, it goes up by a factor of 9. Okay? Because it's a squared function. Okay? Now, let's chit-chat. If I were to draw a graph of distance, okay, so there's maybe 1 meters, 2 meters, up to 5 meters. And this is force between Landon and the fire extinguisher. What would the graph look like? And this is a small force, and this is large force. Roughly, what would the graph look like?
Increase, decrease. I mean, it'd be start out high and then go.
Be a parabola.
Well,
So, first off, would it be a linear function?
No.
Why not? You got D squared, okay? So, that dog won't hunt. Okay? What about that?
No.
Why not? It's not that.
Because it's not that.
Because it's not that?
yes.
Yeah.
Yes.
Because it's not that.
Well,
Because you're dividing by D squared. This would be more like an inverse square root function. Okay?
Yeah.
Which is just
That's what
even
I'm
just
thinking.
root. Okay? So it's not that. So how about,
Yeah.
Yeah. Yeah.
that's,
okay? Now, will it ever hit 0?
no.
So what that means is that Landon's destined for great things. He's going to go to Paris, he's going to go to Moscow, he's going to go to Tokyo, right? He's going to travel the world. No matter where he goes, guess what? He's going to feel a gravitational attraction between no matter where he goes and that fire extinguisher on that wall. Okay? So no matter where he goes, and you all come back for like your 30-year class reunion. Hey, Landon, still feeling that attraction? Yeah, still feeling it, man. Okay?
Oh, no.
Hopefully, I'm not teaching at that point.
That's how rough.
Guys, I'd be like 82. Oh, wow. If I'm still teaching when y'all come back for your 30-year class reunion,
I know a guy, don't worry.
Huh?
what? It's really not where I was going. Okay, if that's
Misinterpretation.
if that's not where I was going, okay?
I'm just helping you out.
Who's your guy?
Don't worry about it.
You can't tell.
That's why he's my guy.
Snitch.
Now, this is, now what do you call a line that approaches this but never touches it?
Asymptote.
Asymptote. Now here's an interesting deal.
Pick up.
So this is how this could play out in terms of asymptotes. And you all have your mathematical definitions and all this good stuff. So let's say that Eli goes to bell rings and McGriddle. McGriddle goes to walk out the door. So when he is like, say 2 meters away from the door, the light is on, okay? When he reaches 1 meter away from the door, I'm going to turn the light back off. When he's at a half a meter, I turn it back on. When he's at 0.25, I turn it back off, okay? So I keep going further and further. So here's the question. When he reaches the door, is the light on or off?
It's gonna be on.
I'd say no.
Because it's gonna flicker so fast that the frequency he won't even be able to tell.
Well, that's what we're experiencing now, but that doesn't matter.
That does matter.
No, it doesn't.
Because
What he's saying is that like you're just gonna keep going.
Pretend
no matter
it
what. I'm never
doesn't.
gonna reach the door.
You're never going to reach the door. That's the point of the story.
Oh, well,
He's never going to reach the point. He will keep dividing this and dividing this and dividing this, and we're all stuck in this room forever because he's never going to get to the door. And this is all on you, big boy, even though you know a guy. Okay? Maybe you know a guy that can come open the
And I can
door.
make a few phone calls, but
Yeah.
But I'll
Wait,
have a long
but
time
that guy
before I
wouldn't
reach
be
the
able to
door.
get to the door either.
Huh?
That guy wouldn't be able to get to the door
Well, I know,
either.
but we're not flipping the light on this side of it. Yeah, that's on the other side. Okay?
Jump to the ceiling.
So that's an interesting thing, though. It's like, okay, and everybody says, oh, he'll never reach the door handle. Well, yeah, you do. I mean, if you didn't, we'd never get anywhere. I mean, you'd never move anywhere because you'd never reach your point. Anyway, so it's going to look something like this, right? Okay, so here's what you're going to do. Now get out the graph and the lab from yesterday. So hopefully your graph looks something like this, okay? Where the center is there, okay? Got this nice elliptical orbit, right? All this good stuff. So what we're going to do is we're going to look at how the relative amount of force changes as Mercury goes around in its orbit, okay? So listen to me, listen to me, listen to me. We're not going to actually calculate the amount of force. We're just going to look at how the relative amount of force changes. So, as Mercury goes around in its orbit around our star, when is the gravitational force between Mercury and the star going to be at its lowest point?
it's furthest away.
Furthest away, right? So obviously when it gets closer, the amount of force is going to go up. So here's what we're going to do. So over here on page 3, up at the top, we need two distances. We need D2 and we need D1. So D2 is going to be when it's at its furthest point. So somebody look through that data and find that biggest radius. I think it's 0.4 something.
0.467.
0.467
Yep.
AUs. And D1 is going to be when it's closest, which is going to be
07.
0.3007 AUs. Okay? So, what we're going to do is we're going to find the relative amount of force that exists when Mercury is closest to the Sun. Okay? So here's what we're going to do. On your equation, or in the lab itself, I've got this idea that you're going to take 1 over, and it's here in the middle, okay? You're going to take 1 over D1 over D2 quantity squared, because it's an inverse relationship with the quantity squared. So, what we're going to do is we're going to take 1 over 0.307 and divide that by 0.467, and then we're going to square that. So somebody take 0.307, divide that by 0.467, square it, and then take the inverse of that. And it should be 2.7. 2.31. Now, this is not 2.31 newtons. Okay, I know I've drilled it into your heads that all force is measured in newtons. Okay, first off, the only units that you have here are astronomical units, and those cancel out. There's no kilograms, there's no meters, there's no seconds squared, nothing. All this is a relative amount of force. Okay, that's it. It's just a relative amount of force. So, what we're saying is that when Mercury is closest to the Sun, that gravitational force is 2.31 times greater than when it's at its furthest point. Okay, that's all we're saying. So here's how I can put this in terms of your lives. Let's say that you have a job and you're earning $10 an hour. And your boss comes to you and says, hey, I'm going to increase your salary, your hourly salary, by a factor of 2.31. Okay? So you're going to go from $10 an hour to what?
23.1.
$23.10 an hour. That's a pretty hefty increase in your hourly wages, right? You're going from 10 to 23.10. Cool. I like this, right? Now, so what we're going to do, and again, this is not newtons. You are not going to keep Mercury in orbit around the star with a force of 2.31 newtons. It is not going to happen, okay? So, here's what you're going to do. You're going to go out here to the furthest point in its orbit. You're going to take a ruler, listen to me, a ruler, okay, a griddle, and you're going to draw a line 1 centimeter long. And what we're going to do is we're going to call that the relative minimum amount of force that exists between Mercury and the Sun. Now, here's one thing I want to get rid of right now. This is the idea that this force only acts in this direction. That force is also being pulled by Mercury is pulling on the Sun with that same amount, but we're just going to draw that vector because it would get really complicated here in the middle. So don't think that this force only goes in one direction. It also pulls it backwards on the Sun. Now, then you're going to go to the point where Mercury is closest in its orbit. And you're going to come in here and you're going to draw that with a line that's 2.31 centimeters long. That is not 2.31 newtons. Okay? It's 2.31 centimeters. Because what we're saying is that when it's at its closest approach, it's 2.3 times greater than when it's furthest away. That's all we're saying. When you get done with that, come over here and pick a couple of other points. I don't care what the points are. Okay? So what you're going to do down here, when you get to number 7, you're going to calculate the relative force at 2 other points, keeping D2 as a constant. You're going to write down those points, and then you're going to draw those vectors pointing towards the Sun. So, Mad Max, stop that. Okay.
So you're a mercenary?
So, you've got the 4 arrows, the point where it's fastest, the point where it's slowest, and then the region where it's speeding up and the region where it's slowing down. Cool with this?
Yes.
Now, this is where we look at like a big idea, okay? And how everything kind of fits together. So here's the Sun, here's Mercury going around. As Mercury goes around in its orbit, is it undergoing centripetal acceleration?
Yeah.
Yes.
Why?
Because it's changing direction.
It's not in a straight line. So you're continuously changing the direction of the velocity vector. So it's undergoing centripetal acceleration because you're changing the direction. But are you also changing the magnitude? Yes, because
Yeah.
it's going slowest.
And you
Okay,
can say
so
that
here
it's
you
also
have
instead of
your
pointing.
smallest velocity vector that's pointing this way. Up at the top, you have your biggest velocity vector, which is pointing this way. So Mercury is actually continuously accelerating in 2 methods. You're continuously changing the magnitude, and you're continuously changing the direction of that vector. So Mercury in no way, shape, or form has constant velocity as it orbits around the Earth. Now, it orbits around the Sun. Even if it traveled in a perfectly circular path, would it still be accelerating?
Yes.
Yes. Why?
It's changing direction.
Still changing direction. If it traveled in a circular path, would the speed remain constant?
Yes.
Yes.
Yes. So when I ask you about speed, I'm just asking about the magnitude. But because it's in this highly elliptical orbit, you're changing 2 things. You're continuously changing the speed, and you're continuously changing the direction. Both of those require a force. Okay. Now, with all that said, you know that centripetal force equals mass v squared over r. So here's the million-dollar question. Is that mass the mass of the sun or the mass of Mercury? Olivia. Mass of the Earth, excuse me, mass of Mercury, mass of the sun.
Mass of Mercury,
Why?
because that's the thing that's actually
Beautiful. This is going to be the mass of Mercury. Is that going to change as Mercury goes around its orbit?
No.
No. Is the velocity going to change as it goes around its orbit? In terms of magnitude? Yes. Is the radius going to change? Yes. Okay. So let's look at this mathematically. I caught it.
Oh, I thought it was hitting the fly.
Huh?
I thought you were like hitting the fly or something.
No. So here's what I want to look at. And this harkens back to Kepler's second law. Kepler's second law says the law of equal areas, right? So when Mercury is closest at this point, what do you know about its velocity? It's fastest. But what about its radius?
It's the lowest.
Shortest.
It's shorter. Okay? So what that means is this. When Mercury is as close as it's going to get, it's going to have a huge centripetal force because it's got a big velocity. Not only does it have a big velocity, but that velocity gets squared, which makes it even more amplified. And it has a small radius. So that means that you've got to have a lot of centripetal force to make Mercury slingshot around the sun. So that's like, you know, if you were little and you had a house that had like a set of steps and a banister, and you run by and you grab a hold of the banister and you like slingshot yourself around, okay? That's basically what the sun is doing with Mercury. Mercury is reaching out, grabbing a hold of it and going, whoa, okay? Wrapping this thing around. Now, you get out here, okay? You get out here. Is this going to require more or less centripetal force once you get to this point? Less. Why? You have two things. You have a smaller velocity and bigger radius. So out here you're going to have a smaller centripetal force because you're going to have the same mass but a smaller velocity, but a bigger radius.
Big old
What? It's a visual way of showing it, right? Okay? So, when you're closer, you have your biggest centripetal force. When you're out here, you have your smaller centripetal force. But here's the kicker. What's creating the centripetal force? Gravity. Is the gravitational force between Mercury and the Sun a constant value?
No.
No.
It's always changing.
Oh! When is the gravitational force the strongest?
Closest.
Smallest radius.
When it's closest. Guess what? That's when you need your most centripetal force. Okay? You can't have it in opposition. In other words, you couldn't need more centripetal force when you're closer, but the gravitational force is at its weakest point. Okay? It wouldn't work. These things have to change hand in hand. So, when you need more centripetal force, you get more gravitational force. When you need a smaller centripetal force, gravity becomes weaker. Okay? So that's why this thing balances out. So this is kind of like driving your hopped up Ford Mustang around a really, really tight corner out in the parking lot. And this is Grandma in her Mini Cooper going really slow, you know, to the donut shop on Sunday morning.
Mini Coopers are
Okay?
fresh, man. Don't sleep on the
You're
coupe.
taking it slow in the Mini Cooper. Here you're in a Ford Mustang hauling. Okay?
Some of those new Mini Coopers are fast.
That's true.
Turbo.
They're fresh, man.
Yeah.
Don't
They
sleep
go
on the
like
coupe.
tiny-
Here's your grandma's Buick. How about that?
Hey, Buick totally reinvented this.
But you got the
It's in the
point.
commercial.
Okay.
Completely reinvented.
Okay. Now,
This is ranch change.
let me kind of go over. Then one other thing that I'm going to turn you loose. So when you get to question number 4, you're going to calculate the gravitational force between Mercury and the Sun. So in number 4, what I want you to do is look at that and go, okay, on average, and this is that radius that I gave you is on average, this is the distance from Mercury to the sun. So what you want to do is go through and say, okay, you've got the mass of Mercury, you've got the mass of the sun, the distance between Mercury and the sun, 5.8 times 10 to the 10th meters. You're going to calculate, on average, the gravitational force between Mercury and the sun. When you get to number 5, you're going to find the amount of centripetal force needed to keep Mercury in orbit around the sun. Now, again, that's going to change, but we're going to treat it as a circular path because it's going to make the math easy. Otherwise, you got to do a bunch of calculus, and you basically end up with the same answer anyway, because on average, this is how far it is. So, here's what you're going to do wrong. Notice that I gave you the orbital period is 88 days. What do the 88 days have to be changed into?
Years.
Seconds.
Seconds.
Oops.
Because newtons are kilograms years.
Kilograms years per second.
Yeah, newtons are kilograms meters per year squared. No,
My bad.
okay? Because you're actually calculating a force. So, when you change the 88 days into seconds, do not round it, okay? Keep that with a whole bunch of significant digits that you're going to use. So, you have enough knowledge right now to finish this, and when you get that done, we'll chit-chat some more. So, let's say, not to scale. Here's Mary on the Earth, okay? Not to scale. And so, one of the things I want to do is figure out how that I can calculate the gravitational attraction between Mary and this rock that we're on, okay? I'm going to give you 3 different options, okay? We're just going to get through the first option today. We'll go through the other 2 options on Monday. So option number 1 is that on the end of Mary's index finger on her left hand, there is a strand of DNA, and within that DNA strand there is a single nitrogen atom. And within that single nitrogen atom there is a proton in the nucleus, 1 of 7. Okay? So we're going to pick that one single proton in the strand of the DNA on the end of Mary's left index finger. Now, that single proton right over here is going to be attracted to every particle that makes up this entire rock that we're on. Okay? So option number 1 is that we go F equals big G, the mass of that single proton. Then let's say underneath Mary there's in the floor there is another proton, okay, that makes up the tile. So that's going to be the mass of another proton, and they're right now about 0.25 meters apart, okay, squared. So we're going to do that between that one proton in the end of her index finger and a single proton that's directly underneath it. Then we're going to do that for every proton that's in the Earth. We're going to do all these calculations. Then we're going to do that for every neutron that's in the Earth. And we're going to do that with every electron that makes up the Earth. So we got to know the location of every proton, electron, and neutron that makes up the Earth. And we're going to do all of that calculation for one single proton in the end of Mary's left index finger in one strand of DNA. Now, how many protons are there in a single nitrogen nucleus?
7.
7. Okay? 7. So then we're going to do that same calculation with another one that's right beside them. And then the third, the fourth, the fifth, the sixth, the seventh. Now, within that, there's also 7 neutrons. So then we need to do that for all the 7 neutrons. Okay? Then we're going to do that for all the 7 electrons. Okay? In one strand. Okay? As just one nitrogen atom. Then we got to do that for the next nitrogen atom, for the carbon atoms, for the oxygen atom, for everything else that make up Mary. Guess what? We're never going to win. Okay? Because we'd have to know so much information, the calculations would be horrible. Okay? So, what we're going to do is we're going to take Mary and we're going to treat her as what's known as a point mass. So imagine that we can take Mary and condense her down so that all, let's say 100 kilograms, are all condensed into one small point. Like we have condensed Mary into one single point. And she's going to be right there. Okay? Mary is what's known as a point mass. Now, the cool thing is, now we're going to do the same thing with the Earth. Okay? So now we're going to take the entire Earth and we're going to condense that into one single solitary point mass. Now, instead of doing an infinite number of calculations between all the particles, we only have to do the calculation once. Because now we're going to treat Mary as a single point mass, and we're going to treat the Earth as a single point mass. Now it becomes a doable calculation. So now we can go F equals big G, which is going to be 6.67 times 10 to the minus 11. Actually, let me write this up here. So we got big G, 6.67 times 10 to the minus 11. We'll make the math easy. Call Mary 100 kilograms. Mass of the Earth, 5.979 times 10 to the 24th kilograms. And then we've got the radius of the Earth, 6.3713 times 10 to the 6th meters squared. Now, don't touch a calculator. Don't not touch a calculator. Do not touch a calculator. All I want to do is what's known as an order of magnitude. Okay, I just want to get a ballpark idea, just a ballpark idea of what this should be. So let's do a little exponent thing, right? So we got 10 to the negative 11th times 10 to the 24th. So if I take 10 to the negative 11th times 10 to the 24th, that gives me 10 to the 13th, right? You should add 10 to, right? Negative 11, 10 to the 24th, 10 to the 13th. And then I've got 100, which is 10 to the second. So 10 to the 13th times 10 to the second gets me 10 to the 15th. So roughly in order of magnitude, I got 10 to the 15th on top, right? Now, I got 10 to the 6th squared. So that's going to get me 10 to the
12.
10 to the 6th squared is going to give me 10 to the 12th. Okay? And realistically, because that's like 6 squared is like 36, probably realistically that's going to be more like 10 to the 13th. But even if we just call it 10 to the 12th. So if I take 10 to the 15th and divide that by 10 to the 12th, I get 10 to the
Third.
So just an order of magnitude, just a ballpark, the gravitational attraction between Mary and the Earth, ballpark, should be something around 10 to the 3rd. So what that means is if I actually do this calculation, and I get like 10 to the 5th or 6th, I've done something wrong. If I get 10 to the negative 3rd, I've done something wrong. Okay? So one of the things that you'll hear me say again and again and again, especially when you do with planetary motion and all of these big numbers, get an estimate of what your answer should be, just based upon order of magnitude. And once you get into the habit of it, it's really not that bad. Because one of the things you'll always do is, you'll see this later why this works. A lot of times you're going to take big G times the mass of the Earth. So right away, 10 to the negative 11th times 10 to the 24th gets you 10 to the 13th. So those two numbers alone kind of get you 10 to the 13th, and then you're kind of off to the races after that. So on Monday, we'll actually go through and actually do this calculation, and then we'll talk about the third way to do the calculation as well. So you have no homework, okay? The test is next Thursday. Just telling you right now. So,
You think we could negotiate a little push Friday? Halloween?
No.
Nick,
I hate
you just ruined the chances. You just ruined the
Halloween.
chances.
I hate Halloween.
I mean, what I meant to say.
No. Dice cast.
Okay.
Okay.
There are pumpkins in
You
this
got
room,
mad
so-
pumpkins in this room.